key assessment of the universe's origin and its ceaseless development is presently at a crucial stage, with cosmology standing up to a portion of its most central vulnerabilities. A critical concentration is deciding the rate at which the universe is growing. For more than 10 years, two significant methodologies for estimating this development have delivered inconsistent results. Ongoing perceptions of the current situation with the universe show that the pace of development, known as the Hubble constant, is around 9% higher than forecasts got from information from the early universe. Researchers had trusted that the James Webb Space Telescope, JWST, the most progressive telescope of all time, would give a conclusive answer to this issue. However, the new, momentous data from JWST has, instead, effectively extended the error, leading to inquiries about the validity of the established cosmological model. This has sparked intense discussions within the academic community about whether new physics are needed to adjust or totally replace the current speculations that have held for more than 4 decades. This possibility is both exciting and alarming, as it suggests that we may be overlooking an essential part of the universe that could decisively change our understanding of its origins. The beginnings of the universe trace back to the Big Bang, a huge explosion that, in an instant, created energy, matter, and space. From this, the universe began as a strongly hot and thick plasma, a combination of matter and antimatter particles. These particles impacted and destroyed each other, yet scientists believe a subtle imbalance allowed slightly more matter than antimatter to form, preventing the universe from annihilating itself. Gravity then condensed the plasma, heating it to the point where sound waves, known as baryon acoustic oscillations, spread through it at speeds greater than around 50% of the speed of light. In the meantime, the dense energy content of the early universe expanded spacetime itself, pushing some matter far enough from the intense heat to survive. As the universe expanded, like an inflatable balloon blowing up, regular matter is thought to have started clumping together around invisible dark matter, eventually forming the first galaxies. These galaxies are believed to be interconnected by an immense cosmic web, connected through dark matter and energy. As the universe continued to expand, both the energy density and the pace of development slowly decreased. However, around 5 billion years ago, galaxies began to recede from one another at an accelerated speed, driven by a mysterious force known as dark energy. The most widely accepted theory for dark energy is that it acts as a steady force woven into spacetime itself, implanted in the fabric of the universe's development. This force, known as lambda in Einstein's theory of general relativity, maintains a constant density as the universe expands, while the density of normal matter decreases over time. Over time, dark energy became the dominant force driving the expansion of the universe, alongside dark matter and regular matter. Together, these forces form the lambda cold dark matter, lambda CDM, model, which describes the universe's development and predicts its possible fate. Heat death, also referred to as the Big Freeze. While many of the model's predictions have been confirmed, the nature of dark energy and dark matter remains unsettled. One of the most significant challenges facing cosmologists is the Hubble tension. Depending on the method used, measurements of the universe's expansion rate yield conflicting results. This inconsistency is pronounced to such an extent that it has become one of the field's most pressing issues. Observations from the early universe suggest a higher expansion rate than the lambda CDM model predicts. These early measurements have been rigorously tested and validated through various observations. According to Nobel laureate astrophysicist Adam Rees, who led the team responsible for the latest JWST measurements, the only possible explanation for the disparity is that our current model is missing something significant. Measuring the expansion rate of the universe requires more than a simple observation. One of the primary methods involves looking at the cosmic microwave background, CMB, which represents the universe's first light, produced roughly 380,000 years after the Big Bang. This imprint is visible across the entire sky and has been mapped extensively between 2009 and 2013 by the European Space Agency's Planck satellite. The map of the CMB shows the universe as nearly uniform, with slight temperature variations marking areas of sequential matter density. These variations reflect the imprint left by baryon acoustic oscillations, which helped cosmologists work out the Hubble constant, yielding an estimate of roughly 67 kilometers per second per megaparsec. To explain this, it means that a galaxy 1 megaparsec away would retreat at 67 kilometers per second, while a galaxy 20 megaparsecs away would retreat at 1,340 kilometers per second. If a galaxy were farther than 4,175 megaparsecs away, it would retreat faster than the speed of light. Another technique for determining the expansion rate involves studying Cepheid variables, stars whose outer layers expand and contract in a regular pattern as they absorb and emit radiation. Discovered by astronomer Henrietta Swan-Leavitt in 1912, this behavior allows cosmologists to measure the star's absolute brightness, which can then be used to estimate their distances. The Cepheid variable method, part of what is known as the cosmic distance ladder, has been a key tool for measuring vast distances across the universe. The first step of this ladder involves measuring nearby Cepheids and confirming their distances. From there, astronomers can measure more distant stars and galaxies by observing their redshift and comparing these measurements, allowing them to compute the Hubble constant. In 2019, Rees and his team used this method to study the Milky Way's closest neighbor, the Large Magellanic Cloud. Their results were surprising, showing a significantly higher expansion rate of 74 kilometers per second per megaparsec compared to the Planck data. While the Hubble Space Telescope made important contributions, its accuracy was limited in crowded regions of space, causing distant Cepheids to blur with neighboring stars. Some cosmologists have proposed that the inconsistency could be due to measurement errors. However, when the James Webb Space Telescope, JWST, was launched in December 2021, hopes were high that it could either resolve or confirm the inconsistency with its 6.5-meter-wide mirror, nearly 4 times the size of Hubble's. Furthermore, JWST's superior infrared capabilities could detect fainter objects and identify a broader range of frequencies. Studies examining Cepheids in the galaxy NGC 4258, among others, revealed results almost identical to Rees's previous findings, with an expansion rate of around 73 kilometers per second per megaparsec. Other measurements, including those by Wendy Friedman using the Hubble Space Telescope and gravitational lensing, returned similar values of 69.6 kilometers per second and 66.6 kilometers per second per megaparsec, respectively. Findings have created a stir in the cosmological community, as noted by cosmologist Ronan Kai from the University of California. Even a small error of just 7 kilometers per second is highly unlikely to be a random mistake, especially given the precision of the measurements. This has led to a division among cosmologists, with some suggesting measurement errors, while others propose the need for new physics, or a combination of both. Kai believes much of the discrepancy lies in the need for new physics. One leading theory is that dark energy's behavior may have evolved over time. If dark energy was once stronger and has gradually weakened, it might have caused the universe to appear smaller in its early stages, leading to a faster expansion rate. Other hypotheses suggest the presence of 2 kinds of dark energy or interactions between dark matter and light. However, these ideas come with complications that many cosmologists are reluctant to accept without further evidence. The discoveries made by the James Webb Space Telescope are not only challenging our understanding of dark energy and dark matter, but also reshaping our views on galaxy formation. By observing galaxies farther back in time than ever before, JWST has revealed galaxies that are much larger and more evolved than anticipated, forming only 300 million years after the Big Bang. These early galaxies, once thought to be mostly composed of young, hot stars, were found to contain heavy elements and even very massive black holes at their centers. These findings challenge the conventional model of galaxy formation, suggesting that the processes of galaxy development may have been faster and more efficient than previously thought. Moreover, these discoveries deepen the mystery of dark matter and dark energy, both of which remain poorly understood despite being dominant components of the universe. Dark matter, which interacts only gravitationally, continues to elude direct detection, prompting ongoing research. Similarly, dark energy, responsible for accelerating the universe's expansion, presents inconsistencies such as the Hubble tension, raising the possibility that its properties may not be consistent across spacetime. Alternative theories suggest dynamic forms of dark energy that could evolve over time, affecting the expansion rate at different stages of the universe's history. To address these mysteries, cosmologists will require both advanced observational tools, like the James Webb Space Telescope and theoretical frameworks capable of integrating new data without discarding the achievements of current models. The implications of JWST's discoveries extend far beyond cosmology, touching on broader astrophysical questions, including the origins of life and the conditions necessary for life on other planets. By studying distant galaxies, cosmologists hope to uncover clues about how Earth-like planets could form around other stars, offering insights into the prevalence and diversity of life across the universe. Looking ahead, the James Webb Space Telescope promises to push the boundaries of our understanding of the universe. Its extraordinary sensitivity and resolution will enable cosmologists to study exoplanet atmospheres more closely, map galaxies more meticulously, and examine the earliest moments of cosmic history with unmatched precision. JWST's ongoing mission is set to continue transforming our appreciation of physics, cosmology, and our place in the universe. Whether uncovering the secrets of dark matter and dark energy, unraveling galaxy formation, or searching for life beyond Earth, the telescope is poised to revolutionize our view of the universe in ways once thought unimaginable. In conclusion, the convergence of cutting-edge technology, theoretical advancement, and precise observation heralds a new era for cosmology and astronomy. JWST's contributions will refine our understanding of the universe's origins, challenge established theories, and open pathways to pivotal discoveries as we continue our journey of exploration. The universe's secrets await, and with JWST leading the way, we are poised to reveal the mysteries of our cosmic legacy and future. The James Webb Space Telescope offers more than just precise measurements of the universe's expansion and detailed observations of early galaxies, addressing some of cosmology's most profound questions. While the possibility that our understanding of the universe could be fundamentally flawed is not new, JWST's precision has sharpened this potential. Integral to the universe's structure are dark matter and dark energy, which remain poorly understood. JWST's ability to study the early universe and observe galaxies that formed just 300 million years after the Big Bang has provided invaluable insights into galaxy formation. These observations challenge the established hypothesis that galaxies should have taken longer to form, suggesting that processes such as star formation and black hole development might have been more efficient in the early universe. Furthermore, JWST's observations are helping to advance the study of dark matter, a mysterious substance thought to play a crucial role in shaping the universe's structure through its gravitational effects. JWST's findings may help us understand how dark matter influenced galaxy formation and possibly uncover new properties of this elusive substance. Beyond dark matter, JWST is also aiding the exploration of exoplanets and the conditions that may allow life to flourish on other worlds. One of the telescope's primary goals is to examine exoplanet atmospheres, looking for signs of habitability or even life. By analyzing the chemical composition of these atmospheres, scientists hope to determine the conditions that may support life elsewhere in the universe. This could provide valuable insights into how Earth-like conditions might exist elsewhere. As JWST continues to gather data, it becomes increasingly clear that we are on the cusp of discovering new physics. Whether unraveling the nature of dark energy, investigating the unexpected complexity of early galaxies, or examining the behavior of dark matter, JWST is opening new avenues for understanding the universe. The telescope is not only refining our current theories but also testing them, challenging researchers to reconsider fundamental assumptions and explore new possibilities. These discoveries are pushing the boundaries of physics, cosmology, and even philosophy as we expand our understanding of the laws that govern our existence. As we continue to study the universe from JWST's perspective, we are not just learning about distant stars and galaxies. We are gaining profound insights into the very nature of the universe itself. The questions raised by JWST's discoveries could lead to a paradigm shift in how we understand the origin, structure, and fate of the universe. As we continue our exploration of the universe through the lens of the James Webb Space Telescope, the potential for a paradigm shift in how we understand the universe becomes increasingly plausible. The telescope's exceptional capabilities have already provided a wealth of data that challenges many of our long-held assumptions about the universe. For example, The detection of early massive galaxies forming just 300 million years after the Big Bang raises important questions about the timescale and processes involved in galaxy formation. These galaxies appear to be far more